The industrial fabrication of a modern automobile tire begins with the strategic procurement and chemical stabilization of a diverse array of elastomeric materials, reinforcing agents, and specialized chemical additives. This initial phase represents the fundamental transition from raw agricultural and petrochemical precursors into a stabilized, uncured rubber matrix known as a compound. A single tire is not a monolithic structure, but a complex assembly of over 60 distinct chemical components, each selected for its specific contribution to the tire's eventual performance in terms of traction, durability, and rolling resistance. The environment of the compounding department is defined by the sterile, clinical precision of the laboratory, the massive mechanical torque of the internal mixers, and the pervasive, heavy aroma of processed polymers and carbon black. The objective of this stage is to create a perfectly homogenized material that possesses the required viscoelastic properties for the subsequent extrusion and calendering phases. The primary structural component is rubber, which is utilized in two distinct forms, natural rubber and synthetic rubber. Natural rubber, derived from the latex of the Hevea brasiliensis tree, is essential for its exceptional tear resistance and low heat buildup under dynamic stress. Synthetic rubbers, primarily styrene butadiene and polybutadiene, are synthesized through the polymerization of petroleum-derived monomers. These synthetic variants are engineered to provide superior aging characteristics and optimized grip on wet surfaces. The ratio of natural to synthetic rubber is a fundamental requirement of the compounding logic, as it defines the tire's classification, whether it is intended for high-performance passenger vehicles or heavy-duty industrial machinery. The integration of reinforcing fillers and the logic of carbon black. While pure rubber possesses high elasticity, it lacks the mechanical strength and abrasion resistance required for contact with the road surface. To provide this structural integrity, the rubber matrix must be reinforced with a high concentration of carbon black. Carbon black is a fine, powdery substance produced through the controlled, incomplete combustion of heavy petroleum products. When integrated into the rubber at a molecular level, the carbon black particles create a reinforcing network that significantly increases the tensile strength and hardness of the material. The choice of carbon black grade, defined by its surface area and structure, is a study in material science. Finer particles provide higher wear resistance but increase the internal friction of the rubber, leading to higher rolling resistance and fuel consumption. In recent decades, industrial logic has increasingly favored the integration of silica, silicon dioxide, as a secondary reinforcing agent. Silica, when combined with specialized silane coupling agents, allows for a significant reduction in rolling resistance without compromising wet traction. This dual filler strategy is a cornerstone of modern green tire technology, requiring absolute precision in the mixing sequence to ensure the chemical bonding of the silica to the polymer chains. The mechanics of the Banbury mixer and the process of mastication. The physical homogenization of these disparate materials is achieved within a massive industrial machine known as an internal mixer or Banbury mixer. This device consists of two counter-rotating pear-shaped rotors housed within a temperature-controlled chamber. The mixer is powered by an electric motor of several thousand horsepower, capable of generating the immense shear forces required to break down the rubber bales and incorporate the powders. The mixing process occurs in 2 or 3 distinct stages to prevent the premature activation of the chemical additives. The master batch stage. In the first stage, the raw rubber, carbon black, and processing oils are introduced into the mixer. The rotors subject the material to intense mechanical working, a process known as mastication, which reduces the molecular weight of the rubber and ensures the uniform dispersion of the reinforcing fillers. The temperature within the chamber rises rapidly due to internal friction, and it must be carefully monitored to prevent the thermal degradation of the polymers. The final mixing stage. Once the master batch has cooled, it is returned to the mixer for the addition of the curative package. This package includes sulfur, which acts as the cross-linking agent during vulcanization, and a series of accelerants and antioxidants. These chemicals are highly sensitive to heat, and if the temperature during the final mix exceeds a specific threshold, typically approximately 100 degrees Celsius, the rubber will begin to scorch or vulcanize prematurely, rendering the material unusable for further processing. Viscoelastic metrology and compound stabilization. The quality of every batch of rubber compound is verified through an exhaustive protocol of viscoelastic metrology. Before the material is released for extrusion, samples are analyzed in a laboratory using a moving die rheometer and a Mooney viscometer. The rheometer measures the torque required to oscillate a rotor within the rubber sample, providing a cure curve that predicts how the material will behave during the final vulcanization process. The viscometer measures the flow characteristics of the compound, ensuring that it possesses the correct plasticity for the high-pressure extrusion and calendering stages. The sound within the compounding department is a rhythmic, low-frequency throb produced by the massive gearboxes and the percussive cycling of the hydraulic rams that feed the mixers. This acoustic environment is a constant indicator of the massive industrial energy being channeled into the molecular restructuring of the rubber. Once verified, the hot rubber is discharged from the mixer onto a two-roll mill, where it is flattened into long continuous sheets. These sheets are treated with an anti-tack solution to prevent them from sticking and are organized into massive wigwag stacks for cooling and storage. The role of chemical protection and longevity additives. To ensure the tire's longevity under extreme environmental conditions, the compound must be protected against the degrading effects of oxygen, ozone, and ultraviolet radiation. This is achieved through the integration of antioxidants and antiozonants. These chemicals migrate to the surface of the tire over time, forming a sacrificial protective layer that prevents the development of dry rot or surface cracking. Additionally, specialized processing oils and plasticizers are added to manage the glass transition temperature, TG, of the rubber. This value determines the temperature at which the rubber transitions from a flexible, grippy state to a hard, brittle state. For winter tires, the TG is engineered to be exceptionally low, ensuring that the rubber remains pliable at temperatures well below 0 degrees Celsius. This level of chemical tailoring is a testament to the precision required in modern tire engineering, where every gram of additive is calculated to optimize a specific performance parameter. The state of the elastomeric matrix at the conclusion of this first chapter is one of chemical readiness. The disparate raw materials have been synthesized into a series of highly specialized compounds, each possessing a verified molecular architecture. The material is no longer merely rubber, it is a standardized technical precursor, ready to be transformed into the various structural components of the tire, such as the tread, the sidewalls, and the apex. The steady throb of the internal mixers and the clinical precision of the rheometers remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the chemical and mechanical discipline required to prepare the polymers for the road. The movement of the stabilized compound from the storage stacks to the extrusion and calendering lines is the next logical step in the manufacturing cycle, marking the end of the chemical synthesis phase and the beginning of the mechanical component fabrication. The movement of the cold, stabilized rubber sheets from the compounding department to the component fabrication lines marks the beginning of the mechanical shaping phase in the industrial life cycle of a tire. In this stage, the homogenized elastomeric compounds are transformed into specific, high-precision semi-finished components, the tread, the sidewalls, and the rubber-coated cord layers that form the tire's structural skeleton. This phase is governed by the principles of fluid dynamics and high-pressure thermal processing. The environment is characterized by the rhythmic, low-frequency hum of massive electric motors, the persistent hiss of industrial cooling water, and the clinical precision of laser-guided metrology systems. The objective is to produce components that possess absolute dimensional consistency, as even a microscopic deviation in thickness or width would compromise the balance and safety of the final assembly. The kinetics of hot feed extrusion and the formation of the tread profile. The fabrication of the tread, the critical interface between the vehicle and the road, is achieved through a process known as extrusion. The uncured rubber compound is fed into a massive screw-type machine called an extruder. As the internal screw rotates, it subjects the rubber to intense mechanical shear and thermal energy, transitioning the material back into a highly plastic, flowable state. This is not merely a mechanical movement, it is a thermodynamic preparation that ensures the rubber can be forced through a specialized shaping tool known as a die. In modern high-performance tire manufacturing, a single tread profile is often composed of several distinct rubber compounds. This is achieved through co-extrusion, where multiple extruders feed into a single head. The cap compound, the outermost layer, engineered for maximum traction and abrasion resistance. The base compound, the internal layer, designed for low heat buildup and structural stability. And the wing tips, specialized compounds on the edges of the tread that facilitate a seamless bond with the sidewalls. As the composite rubber ribbon exits the die, it assumes its final geometric profile. The logic of the die design is a study in fluid mechanics, as the shape of the die must compensate for the die swell, the natural tendency of the rubber to expand slightly once the pressure is released. The extruded ribbon then travels through a series of long cooling tanks filled with temperature-controlled water. This rapid thermal reduction freezes the dimensions of the tread and prevents any unintended deformation. The precision calendering of textile and steel reinforcing cords. While the rubber provides the elasticity and grip, the structural strength of the tire is provided by an internal network of reinforcing cords. These cords are integrated into the rubber matrix through a high-pressure process known as calendering. A calender is a monumental machine consisting of 3 or 4 heavy-duty steel rollers arranged in a vertical or horizontal manifold. These rollers are heated internally with high-pressure steam and are polished to a mirror finish. There are 2 primary types of reinforcing substrates processed in the calendering department. Textile cords, manufactured from high-tenacity fibers such as polyester, rayon, or nylon. These cords provide the tire with flexibility and impact resistance. Before calendering, the fabric is treated with a specialized adhesive dip to ensure a permanent chemical bond with the rubber. Steel cords, consisting of fine, high-carbon steel wires twisted into complex cables and coated with a thin layer of brass. The brass coating is critical as it facilitates a chemical reaction with the sulfur in the rubber compound during vulcanization, creating an unbreakable metallurgical bond. The logic of the calender is to friction the rubber into the interstitial spaces between the cords. 2 thin sheets of rubber are fed into the rollers simultaneously with the cord layer. Under immense pressure, the rubber is squeezed into the fabric or wire, creating a perfectly flat rubber-encapsulated sheet. The thickness of this sheet is monitored by beta ray or X-ray sensors that provide real-time feedback to the roller gap actuators, ensuring a precision within 0.01 millimeters. The fabrication of the bead core and apex. The terminal interface between the tire and the vehicle's rim is the bead. The bead must be exceptionally rigid and non-extensible to ensure that the tire remains securely seated under high-speed cornering and braking forces. The core of the bead is manufactured from high-tensile steel wire that is coated with rubber and wound into a multi-layer ring of a specific diameter. Once the wire ring is formed, it is fitted with a triangular rubber component known as the apex. The apex serves as a structural transition, providing a gradual increase in stiffness from the rigid bead to the flexible sidewall. This assembly is then wrapped in a protective fabric known as a chafer, which prevents the rim from abrading the rubber. The movement of the bead winding machinery is a rhythmic, high-speed sequence of wire feeding, rubber coating, and precision cutting. The sound in this area is a percussive metallic click as the wire is severed at the conclusion of each winding cycle. Metrological verification and the logic of semi-finished storage. Every meter of extruded tread and calendered cord is subjected to an exhaustive metrological interrogation. Automated laser scanners measure the width, thickness, and symmetry of the components, while ultrasonic sensors detect any internal voids or delaminations. If a component fails to meet the specified technical tolerance, the system automatically marks it for rejection and recycling as scrap rubber. The verified semi-finished components are then organized into large specialized cassettes or storage racks. To prevent the uncured rubber from sticking to itself, the components are interleaved with liner fabric, a specialized textile with a non-stick coating. These racks are then transported to the tire building department. The environment of the storage area is one of monumental stillness, a temporary pause in the industrial flow before the final assembly phase. The state of the elastomeric and metallic substrates at the conclusion of this second chapter is one of geometric maturity. The amorphous rubber compounds and raw cords have been transformed into standardized, high-precision structural elements. They are no longer disparate materials, they are the individual components of a complex mechanical system, possessing the verified dimensions and chemical readiness required for the building of the green tire. The steady hum of the extruders and the rhythmic clatter of the calenders remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the mechanical discipline required to prepare the materials for the final synthesis. The movement of the cassettes from the storage area to the tire building machines is the next logical step in the manufacturing cycle, marking the end of the component fabrication phase and the beginning of the structural assembly. The progression of the semi-finished components from the storage cassettes to the tire building department represents the most critical synthesis phase in the industrial fabrication of an automobile tire. In this stage, the individual elements, the inner liner, the body plies, the beads, the sidewalls, and the tread are integrated into a single cohesive mechanical unit. This process is conducted on a highly sophisticated apparatus known as a tire building machine, or TBM, a device characterized by its rotating drums, high-precision laser alignment systems, and coordinated robotic applicators. The environment is one of extreme mechanical discipline, defined by the rhythmic clicking of pneumatic actuators, the low-frequency whirring of the drum drives, and the sterile hiss of vacuum suction cups. The objective is to assemble these components with absolute concentricity and symmetry, as even a minor misalignment during the building phase would manifest as a significant vibration or structural failure in the finished product. The assembly logic is typically divided into two distinct stages, which may occur on a single machine or across two separate specialized units. The first stage involves the creation of the tire's carcass, the internal skeleton that provides structural integrity and contains the internal air pressure. The process begins with the application of the inner liner onto a collapsible building drum. The inner liner is a specialized sheet of halogenated butyl rubber, engineered for its exceptional impermeability to air and moisture. Because modern tires are tubeless, this layer must serve as the primary pressure-retaining membrane, ensuring that the compressed air does not migrate into the fabric or steel layers of the tire structure. The mechanical layering of body plies and the anchoring of the beads. Once the inner liner is secured, the body plies, the calendered textile sheets described in the previous chapter, are wrapped over the drum. For a standard passenger tire, 2 or more layers of ply are applied, with the fabric cords oriented radially, perpendicular to the direction of travel. This radial orientation provides the tire with its characteristic flexibility and high-speed stability. The logic of the ply application involves a precision overlap splice, which must be managed to within 1 or 2 millimeters to ensure that there are no localized areas of weakness or excessive mass. Following the ply application, the bead setter mechanism moves into position. This automated assembly holds the rigid steel and apex bead rings and presses them against the ends of the drum. A series of inflatable rubber bladders then expand, folding the edges of the plies around the beads. This turn-up operation is essential as it physically anchors the fabric skeleton to the rigid steel cores that will eventually seat against the vehicle's rim. The sound in this area is a rhythmic sequence of pneumatic inflation and mechanical folding, a testament to the scale of the force required to manipulate the uncured rubber and steel. The integration of the belt package and the tread ribbon. While the first drum is assembling the carcass, a secondary drum, often referred to as the belt and tread drum, is simultaneously preparing the outer reinforcement package. This package consists of 2 or more layers of steel cord belts and the extruded tread ribbon. The steel belts are applied at specific opposing angles, typically between 20 and 30 degrees relative to the tire's centerline. This triangulated architecture provides the tire with its lateral stiffness required for cornering and prevents the tread from expanding excessively at high centrifugal velocities. Once the belt package is complete, the tread ribbon is applied. Because the tread is a thick, multi-compound component, its application requires a high degree of tension control to prevent the formation of air pockets between the layers. A specialized stitcher roller then travels across the surface of the tread, applying a calculated pressure to expel any trapped air and ensure a permanent mechanical bond. The transition from the application of the thin steel belts to the massive tread ribbon is a study in industrial kinetics, managed by a centralized computer system that synchronizes the drum's rotation with the feeder's velocity. The toroidal transformation and the consolidation of the green tire. The final sequence of the building process is the shaping and consolidation phase. The carcass drum and the belt tread drum move into a single longitudinal axis. The carcass, which at this point is a simple cylinder, is inflated using a high-pressure air bladder, expanding outward into a toroidal or donut-like shape. As it expands, it makes contact with the interior of the belt and tread package, which is held in place by a specialized transfer ring. The two assemblies are then stitched together using a series of automated rollers that move from the center of the tread towards the sidewalls. This consolidated assembly is now technically referred to as a green tire. The term green does not refer to color, but to the uncured plastic state of the rubber. The green tire possesses the final dimensions and shape of an automobile tire, but it remains soft and malleable, lacking the durability and tread pattern that will be conferred during the subsequent vulcanization stage. The sound of the final consolidation is a deep, resonant thud as the air bladder expands, followed by the high-speed whirring of the stitching rollers. Every green tire is then automatically removed from the machine by a robotic extractor and placed onto a conveyor line for its first exhaustive inspection. Metrological interrogation and the geometry of the uncured carcass. The green tire must undergo a rigorous geometrical verification before it can proceed to the curing press. An automated inspection station utilizes a battery of laser line sensors and high-definition cameras to measure several technical parameters. Concentricity. The system verifies that the tire is perfectly circular and that the beads are equidistant from the center line. Mass distribution. Because the uncured rubber is soft, the system checks for any localized thickness variations that could lead to an imbalanced tire. Splice integrity. Every mechanical joint where the plies or tread ends meet is inspected to ensure it has not opened during the shaping process. If the green tire fails any of these metrological checks, it is diverted to a rework station or scrapped for material recovery. The logic of this inspection is absolute. If a defect is allowed to remain in the green tire, it will be permanently locked into the structure during vulcanization, resulting in a defective finished product. The environment of the inspection station is one of quiet, clinical scrutiny, a sharp contrast to the high-energy kinetics of the building machine. The state of the elastomeric and metallic matrix at the conclusion of this third chapter is one of structural unity. The disparate semi-finished components have been synthesized into a complex, multi-layered toroidal unit. The green tire is no longer a collection of parts, it is a prototype of the final product, possessing the internal architecture required for high-speed performance. The steady clicking of the pneumatic valves and the rhythmic rotation of the building drums remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the precision required to assemble the foundations of automotive safety. The movement of the green tire from the building machine to the curing department is the next logical step in the manufacturing cycle, marking the end of the assembly phase and the beginning of the chemical synthesis known as vulcanization. The arrival of the green tire at the curing department represents the definitive metallurgical and chemical climax in the fabrication process. At this juncture, the soft plastic assembly of uncured rubber and steel is transformed into a high-strength, elastic, and durable technical component through a process known as vulcanization. This phase is governed by the principles of organic chemistry and thermodynamics, specifically the cross-linking of polymer chains in the presence of heat, pressure, and sulfur. The environment is characterized by the monumental scale of the curing presses, the rhythmic release of high-pressure steam, and a pervasive, heavy aroma, the industrial equivalent of a slow-cooked meal, but with significantly higher stakes and less seasoning. The objective is to convert the temporary mechanical bond of the green tire into a permanent chemical structure capable of enduring the immense stresses of automotive operation. The primary instrument of this transformation is the curing press, a massive hydraulic or mechanical apparatus containing a two-part steel mold. The green tire is automatically loaded into the open mold by a robotic manipulator. Once positioned, a specialized internal component known as the curing bladder, a heavy-duty rubber membrane, is inserted into the center of the tire. As the press closes with a force that can exceed 100 tons, the bladder is inflated with high-pressure steam or hot water, forcing the exterior of the green tire against the intricate patterns carved into the interior of the mold. The kinetics of the vulcanization reaction and sulfur cross-linking. The logic of vulcanization, discovered by Charles Goodyear and refined by a century of industrial practice, involves the creation of chemical bridges between the individual polymer chains of the rubber. In its uncured state, the rubber molecules are long, tangled strands that can slide past one another, resulting in the material's plasticity. During the curing cycle, which typically lasts between 10 and 15 minutes for a passenger tire, the temperature is elevated to approximately 140 to 180 degrees Celsius. Under these conditions, the sulfur atoms introduced during the compounding phase become chemically active. They break their internal bonds and form covalent links between the adjacent rubber polymers. This creates a three-dimensional molecular network that prevents the chains from sliding, effectively locking the material into a permanently elastic state. This restructuring is an exothermic process, meaning it generates its own internal thermal energy as the new bonds are formed. The management of this thermal cycle is absolute. If the temperature is too low, the tire will be undercured and lack durability. If it is too high, the rubber will undergo thermal degradation, leading to a brittle and unsafe product. The formation of the tread pattern and sidewall metrology. As the internal bladder expands, it exerts an outward pressure of approximately 200 to 300 pounds per square inch. This immense force serves two technical functions. Tread imprinting. The soft rubber of the tread is forced into the negative recesses of the mold, forming the sipes, grooves, and blocks of the tire's tread pattern. This geometry is essential for water evacuation, traction, and noise reduction. Sidewall identification. The rubber of the sidewall is pressed against the mold's peripheral plates, which contain the embossed data required by international regulations, including the tire size, load index, speed rating, and safety warnings. The sound within the curing hall is a rhythmic percussive sequence of hissing and clanking. Every few minutes, a press reaches the conclusion of its cycle and opens with a sudden release of steam, a process known as the blowdown. The cured tire, now a steaming, black, and resilient object, is ejected from the mold and captured by a mechanical arm. At this stage, the tire is at its maximum thermal energy and must be handled with care to prevent any localized deformation before it stabilizes. Post-cure inflation and the stabilization of the carcass. For many high-performance tires, the curing process does not end with the opening of the press. To prevent the internal textile and steel cords from shrinking or distorting as they cool, the tire is immediately moved to a post-cure inflation station. In this area, the hot tire is mounted on a specialized rim and inflated to a high pressure, where it remains for several minutes until its temperature falls below the critical transition point. Technical note: the PCI process is a study in dimensional stability. By holding the tire in its expanded state during the final cooling phase, the manufacturer ensures that the internal tension of the plies and belts is perfectly balanced. This minimizes the risk of sidewall indentations or radial runout that could affect the vehicle's handling. The sound of the PCI station is a steady, high-frequency hum from the cooling fans, occasionally interrupted by the sharp snap of the pneumatic valves as tires are mounted and dismounted. The atmosphere is one of transition. The tire is moving from the chemical domain of the press to the mechanical domain of final inspection. The final metrological interrogation and finishing operations. Once the tire has cooled to ambient temperature, it undergoes a series of finishing operations. The most visible of these is the removal of vent spews, the small rubber whiskers formed by the tiny holes in the mold that allow air to escape during the expansion. These are trimmed by an automated machine equipped with high-speed rotating blades. The tire is then subjected to its first exhaustive metrological interrogation in its finished state. An automated system utilizes laser-guided sensors to measure the uniformity and balance of the tire. Radial and lateral force variation. The tire is spun against a load wheel to simulate the forces it will encounter on the road. The system detects any microscopic fluctuations in the tire's roundness or internal stiffness. Dynamic balance. The tire is spun at high speed to identify any mass imbalances. Even a deviation of a few grams is recorded and, if necessary, corrected or marked for rejection. The state of the elastomeric and metallic matrix at the conclusion of this fourth chapter is one of functional completion. The green assembly of the previous stage has been permanently synthesized into a high-performance safety component. The tire now possesses the traction, durability, and structural integrity required for millions of rotations on the highway. The steady roar of the curing hull and the rhythmic hiss of the steam lines remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the thermodynamic discipline required to cook the foundations of automotive movement. The movement of the finished tire from the curing hall to the final labeling and distribution warehouse is the next logical step in the manufacturing cycle, marking the end of the fabrication history and the beginning of its service life. The movement of the vulcanized tire from the post-cure inflation station to the final inspection department represents the terminal phase of industrial verification. In this stage, the tire is subjected to an exhaustive battery of non-destructive tests designed to identify microscopic internal defects and ensure absolute compliance with global safety standards. This environment is characterized by the sterile, clinical precision of high-resolution imaging systems, the high-velocity whirring of testing drums, and the rhythmic scanning of automated laser metrology. The objective is to certify that the complex assembly of rubber, steel, and textile, now permanently synthesized, possesses the required internal symmetry and rotational balance to endure billions of cycles on the road. Internal structural interrogation via automated X-ray radiography. The most critical technical verification involves the visualization of the tire's internal skeleton. Because the rubber is opaque, traditional visual inspection cannot detect a misaligned belt, a frayed cord, or a microscopic air pocket trapped between the layers. To address this, every high-performance tire passes through a lead-lined X-ray inspection chamber. The tire is mounted on a rotating spindle and subjected to a high-energy beam of radiation. The resulting radiographic images are analyzed in real time by a centralized computer system using specialized computer vision algorithms. This interrogation focuses on several key parameters: belt centering and alignment. The system verifies that the two steel belts are perfectly centered relative to the tread's midline. A deviation of even 3 or 4 millimeters could cause the tire to pull to one side or wear unevenly. Wire spacing and angle. The algorithm measures the distance between the individual steel cords in the belts. If the cords are too close or too far apart, the tire's structural integrity is compromised. Foreign inclusions. The X-ray can detect any microscopic metallic or high-density particles that may have accidentally entered the rubber during the compounding or building phases. If an internal anomaly is detected, the tire is automatically diverted to a scrap chute, as structural defects within the belt or carcass cannot be repaired. The sound in this area is a muted electronic chirp as the scanner communicates with the sorting system, a manifestation of the silent, invisible scrutiny required for automotive safety. High-velocity uniformity and dynamic balance assessment. Once the internal structure is verified, the tire enters the uniformity and balance station. This process is a study in rotational dynamics. Even if a tire looks perfect, microscopic variations in mass distribution or rubber stiffness can lead to vibration and noise at highway speeds. Uniformity testing. The tire is inflated and pressed against a massive, high-precision load wheel that simulates the weight of a vehicle. As the tire rotates, sensors measure the radial force variation, the subtle up and down force changes, and lateral force variation, the side-to-side movements. The logic of this test is to ensure the tire is round when rotating, a state that is often different from being round when stationary. Dynamic balancing. The tire is spun at high speed on a specialized axis. If the mass is not perfectly distributed around the circumference and across the width, the system identifies the exact location and weight of the imbalance. Technical note: unlike wheels where lead weights can be added to correct balance, an imbalanced tire is often a result of a heavy spot created by an overlapping tread splice or a localized concentration of rubber. If the imbalance exceeds a threshold of a few grams, the tire is rejected or marked as a substandard unit for low-speed applications. The sound of the uniformity station is a powerful, low-frequency hum as the load wheel engages, followed by the high-pitched whistle of the tire as it accelerates to its testing velocity. Laser-guided metrology and visual surface verification. The final step in the metrological sequence is the verification of the tire's exterior geometry and cosmetic appearance. Automated laser line sensors sweep the surface of the tread and sidewalls, measuring the runout and looking for any bulges or depressions. A bulge in the sidewall often indicates a broken carcass cord, while a depression can be a sign of a structural overlap. Following the automated scan, a human inspector conducts a final tactile and visual check. This is the only point in the process where human intuition is utilized to detect subtle cosmetic flaws, such as mold skin issues or surface blemishes that might not be captured by the sensors. The inspector verifies that the DOT code, speed rating, and size markings are clear and accurate. The environment of this station is one of focused silence, where the only movement is the slow, methodical rotation of the tire under high-intensity inspection lights. Logistical identification and global deployment. The state of the tire at the conclusion of this fifth chapter is one of functional maturity and certified safety. The tire is now a high-technology industrial product, possessing a unique digital identity. Labeling and barcoding. A specialized adhesive label is applied to the tread, containing the tire's technical specifications, environmental rating for fuel efficiency and wet grip, and a unique barcode. In many modern facilities, a small RFID chip is embedded within the sidewall rubber, allowing for lifelong traceability from the factory to the recycling center. Logistical sorting. The tires are organized into stacks or pallets based on their size and destination. Automated sorting conveyors move the tires into the warehouse, where they are staged for transport by sea, rail, or heavy-duty truck. The state of the elastomeric and metallic matrix is now of permanent structural realization. The molecules of natural and synthetic rubber, which were once liquid and amorphous, are now locked into an unbreakable three-dimensional network. The steel cords, which were once raw wire, are now the high-tensile skeleton of a vehicle's contact patch. Every tire leaving the facility represents a triumph of chemical engineering and mechanical precision, a standardized solution for the management of friction and the protection of life. The steady hum of the logistical conveyors and the rhythmic clicking of the barcode scanners remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the discipline required to manufacture the foundations of global mobility.